The main job of the lungs is gas exchange, pulling oxygen into the body and getting rid of carbon dioxide. Normally, during an inhale, the diaphragm and chest muscles contract to pull open the chest, and that sucks in air like a vacuum. And then during an exhale, the muscles relax, allowing the lungs to spring back to their normal size and push that air out. When we breathe in, oxygen-filled air from the environment enters through the nostrils, goes down the airways, and finally reaches the alveoli, which are the tiny air-filled sacs in the lungs where oxygen finally moves into the blood. The amount of oxygen in the alveolus equals whatever enters from the airways, minus whatever moves into the blood. And that general relationship is essentially the alveolar gas equation. Now, the total pressure of the air in the alveolus is equal to the atmospheric pressure outside, or PATM. But unlike atmospheric air, the air inside the alveolus gets saturated with water vapor after traveling through the moist airways. The partial pressure of water vapor is P vapor. So in the alveolus, the total pressure, which is equal to the atmospheric pressure, is equal to the pressure of water vapor plus the pressure of the mixture of gases. So after rearranging, the total alveolar pressure exerted from all of the gases except water vapor is equal to the atmospheric pressure minus the partial pressure of the water vapor. Alright, so let's take a step back for a sec. And let's look at this mixture of gas particles, red being oxygen and blue being carbon dioxide. The partial pressure of one of these gases is proportional to the fractional concentration of that gas in the mixture. In other words, the number of one type of gas molecule to all of the gas molecules. So in this case, carbon dioxide would have a fractional concentration of 0.3, since it accounts for 30% of the gas molecules. And oxygen would be 0.7, since it accounts for the remaining 70%. The reason these are proportional to the partial pressure is that more molecules are more likely to bounce around and hit the container. With our example, we see way more oxygen balls bouncing off the container as carbon dioxide balls. And this is just because there are more of them. And every time one of those bounces off the container, they exert pressure. So based on that, you'd expect the oxygen to exert more pressure than the carbon dioxide. And this is proportional to their fractional concentrations. As an example, let's say that the total pressure in the box was 20 millimeters of mercury. That means that the partial pressure of oxygen would be 0.7 times 20 equals 14 millimeters of mercury. And carbon dioxide would be 0.3 times 20, or 6 millimeters of mercury. We're just multiplying the total pressure by the fractional concentration. So essentially, this equation is the fractional concentration of oxygen in the air, or FO2, times the total pressure of the mixture of gases, or P gases. And since we're looking at inspired air, let's say that the partial pressure of inspired air is PiO2, and the fractional concentration of oxygen in the inspired air is FiO2. Now, remembering our equation that we found from before that takes water vapor into account, the partial pressure of oxygen from the inspired air, or PiO2, will be equal to the fractional concentration of oxygen in the inspired air times the quantity atmospheric pressure minus the pressure of the water vapor. Alright, so let's jump back to that alveolus. We've got an equation for partial pressure of air coming into the alveolus. What about on the other side? The partial pressure of oxygen in the arterioles, with little a for arteriolar, where you have oxygen dissolving into the blood, essentially how much oxygen is consumed by the body. In calculating how much oxygen is consumed by the body, we make use of the respiratory quotient, abbreviated as big R. Put simply, this is just the ratio of carbon dioxide molecules produced by the body to oxygen molecules consumed by the body. The value of big R depends on things like our diet. And for a person consuming a healthy mix of carbohydrates, proteins, and fats, R is around 0.8. In other words, for every 10 molecules of oxygen that we consume from the blood, we produce 8 molecules of carbon dioxide. So, going back to the alveolus, 10 molecules of oxygen move from the alveolus and into the blood, and then get replaced by 8 molecules of carbon dioxide. So essentially, if we know how much carbon dioxide is in the alveolus, and we know the respiratory quotient R, we can figure out how much oxygen moved into the blood by rearranging this equation. Also, remember that partial pressure is proportional to the fractional concentration. So essentially, this becomes partial pressure of oxygen dissolved in the blood, or again, little a for arterial, equals partial pressure of carbon dioxide dissolved in the blood divided by R. Now, these 8 molecules I've drawn in the alveolus actually represents the partial pressure of carbon dioxide in the alveolus, where P little a CO2 from our equation would be the carbon dioxide dissolved in the blood down here. But it actually turns out that the carbon dioxide is so highly soluble in water or blood that its partial pressure in the alveolus is equal to its partial pressure in the blood. So the partial pressure of oxygen that's dissolved in the blood also equals the partial pressure of carbon dioxide in the alveolus divided by R. So now let's jump back to the beginning, and remember how we said that the amount of oxygen in the alveolus equals the amount in the airways minus the amount taken into the blood. Since again, partial pressure is proportional to the concentrations, the partial pressure of oxygen inside the alveolus, or P big AO2, equals the partial pressure of inspired oxygen, PiO2, minus the partial pressure of oxygen going into the blood, P little AO2. And now we have all the pieces that we need. And after plugging in partial pressure of inspired oxygen and partial pressure of oxygen in the arterioles, we end up with the partial pressure of oxygen in the alveolus is equal to the fractional concentration of inspired oxygen times the quantity atmospheric pressure minus the pressure of the water vapor minus the partial pressure of carbon dioxide in the alveolus divided by R. And this is the alveolar gas equation. And it looks kind of scary at first, but if you plug in some real life numbers, then it gets pretty simple. Normal air has about 21% oxygen, so the fractional concentration of inspired oxygen is 0.21. Atmospheric pressure is 760 millimeters of mercury. Water vapor pressure is 47 millimeters of mercury. And R is 0.8. So essentially the equation becomes partial pressure of oxygen in the alveolus is equal to 150 minus 1.25 times the partial pressure of carbon dioxide in the alveolus. Alright, as a quick recap. The alveolar gas equation describes the relationship between the partial pressure of oxygen inside the alveolus to the partial pressure of carbon dioxide in the alveolus, which remember is equal to the partial pressure of carbon dioxide in the arterioles, or P little AO2.